Okay, off we go. Oh, yeah, I always forget to check the record. There we go. Okay, so we are back in business. Okay, so here's where we, picking up where we left off. We're talking about flux integrals and various tools for computing flux integrals, which is, by the way, just a term for vector surface integral. I mean, the motivation that we have from, why did we write down vector surface integrals in the first place was we were interested in the question of computing flux. So sometimes people call them flux integrals. A few more related tools. One of them is what I'm going to call lucky coincidences, or I've referred to this kind of thing in the past as geometric good fortune. Just kind of a heads up thing. I mean, just always head on a swivel. If you've been asked to compute a flux, don't forget that ds vector is just the unit normal, the orientation unit normal vector times the ds scalar. And sometimes, surprisingly often, that orientation unit normal, you can just read it straight off of the picture. And in this case, it's and I have a typo here. It's exactly just the position vector r divided by 3, because that's a sphere of radius 3. And the position vector is perpendicular to the surface, and again, geometry, boom, there you go. So when you write that in there, right, you take that formula for the normal vector, pop it right on in there, and then notice your integral just kind of disappears. Right? Now, we got lucky. You can't count on that. I'm not saying that will always happen. What I am saying is that it happens more than you would expect from randomly, right? Because the world's full of circles and spheres and planes and things that are geometrically convenient. And so, big win. If you're not on the lookout for this kind of thing, then you'll get in trouble sometimes. So here's a related example. Here we have a bit of a strange surface. This surface here, it's a part of y equals 3. Here's the plane y equals 3. It's not all of y equals 3. It's just the part that satisfies that inequality. And, it's a quartic, right? That's inconvenient. A little bit scary that we're going to have to worry about, what is the exact shape here, and am I going to have fourth roots when if I parameterize and solve for either z as a function of x or x as a function of z. It's a little bit scary at a glance, right? So, okay, well, yeah, it could be, but let's look for convenient, geometric good fortune. And here's the thing. The fact that y equals 3 immediately tells me 2 freebies. Just freebies, right? For one thing, because y equals 3, you plug that into there and you realize that this second coordinate of the vector field is 0. And so I can pop that in there like so. All right, just boop, instantaneous. Just capitalizing on what we have to work with. So don't leave the money on the table, right? I mean, if something like that comes up, be on the lookout for it. Right? Secondly, because y equals 3, because this is a plane, and because it says right here that the surface is oriented in the positive y direction, well, I know all about planes like that. I know exactly how they're arranged in space, and I know exactly what that normal vector is then. So again, we get kind of lucky, and I can instantly write that down. I haven't parameterized anything. Right? So simple geometry and geometry, algebra, depending on how you want to look at it, gives us a tremendous amount of free information. And again, we get lucky and everything just disappears. That dot product is 0. And so our answer is 0. So again, heads up, be on the lookout for this kind of good stuff. All right.
moving along. I'm going to try to be as quick as I can on this one. It's just like the story we told with coordinate line integrals. Remember, the big idea of a coordinate line integral is it's kind of just an alternative notation for a vector line integral. Well, likewise, a coordinate surface integral is just an alternative notation for a vector surface integral. It's going to come about by taking our vector differential, rewriting it. None of that's new. That's all old news. And we're just going to write it out in coordinates. Right? That's the big first step. Just take what we have written with vector notation, which, by the way, as a broad stroke, I mean, in very many cases, it's a good thing to think in terms of vectors, right? Vector algebra, and not sort of reflexively rewrite everything in terms of coordinates. But in this case, kind of interesting what turns out if you write this in terms of coordinates, and if you just kind of multiply it out. I mean, this thing here, if you just kind of, this cross product, you just kind of crank it out, you end up, and we've made this observation previously, that weirdly, you get a couple of seemingly two-dimensional change of variables stretching factors, mysteriously. Okay, so that noted, let's ask reasonably, when I, cross multiply here to turn this into this, what should we call that? Now, to be fair, for the moment, we haven't really established if there is really a two-dimensional change of variables happening. So, turns out there is. If you look at it from the right point of view, we don't have time to go down that road. It makes me sad because it's a really beautiful little argument. But I think you'll probably buy it if I say, well, it's like those cancel. And even if only as notation, it makes sense to call that dy dz. And again, there's really good reasons underlying this that we don't have time to talk through. 20-minute conversation. And so likewise, here and here. So again, just like we did with line integrals, taking this sort of new version of the ds vector, and by the way, don't forget your vector field has coordinates also, and then you crank out this dot product, and the dot product gives you that. So this is what we call a coordinate surface integral. And individually, each one of these three terms you can call a coordinate surface integral. So what's the upshot? How does this affect y'all? Well, it's kind of the same as with coordinate line integrals. It's not really going to help you very much in this course. It's not as convenient to write in most cases. It's not as intuitively, immediately satisfying. I mean, there's something really nice about looking at that and saying, that represents the flow of a fluid. Simple, crisp interpretation. And this represents all of the relevant characteristics of a particular little piece of surface. It represents how big it is and how it's oriented in space. So you lose that, and there's kind of, what are you going to do? So basically we have here a bulky and unintuitive notational alternative, which I don't think in most cases we're really in the market for. But to be clear, this is also very important. This is what differential forms kind of look like. Not exactly, but it's pretty close. Powerful ideas with differential forms. So there are great reasons to like this notation. They just don't show up in this course. Right? Yes?
So do we need to be able to solve something like that?
Yeah. Absolutely. Well, you need to be able to deal with this satisfactorily, right? So in other words, if you encounter this, whether Kali writes it in the book or if I, on some wild hair, decide to put it on a test or whatever, you need to know what to do with it. Right? Because that is in your future. You're going to see this kind of notation, and you can't just be waylaid by a notation we don't like. Right? So do make sure to remember that when you see something like this, that all of this stuff is just code for the ds vector, and that therefore all of this stuff can be interpreted as just the coordinates of the vector field.
Yeah. And then, whether you compute it from this notation or from that, it's all the same stuff. We've got formulas for everything.
So plug and chug however you prefer, but that's the best way to think about it for our purposes, I think. Yeah.
Also, at the risk of perhaps asking a better question, how do we, when we see that, or in general, what is geometrically, what are we looking at?
You mean with dy dz?
Yeah.
Yeah. That's
especially the sum of the different.
No, I understand. Yeah. So, right. So let me say, your question makes my point. It is hard to figure, what does that, how should I think about this? And there are answers to that question, but that's what I'm going to call it's a detour that we don't have time for. It's a detour that you don't need to worry about. I think everything for your purposes, for the purposes of, engineering really, I think it's plenty good enough to just sort of think of it like this. That's a weird notation to represent a flux integral. Yeah. So I wish I had time to answer your question, but it's not going to really fit in the course.
My question was more around, geometrically, what do we look at to know that this is what then, what is the picture or the graph that we're looking at that tells us that what I'm computing will be this?
Oh, you're wondering in what scenario would you, what question would you be looking at where you would naturally do that?
Yeah.
There isn't one.
Okay.
Yeah, because it's exactly the same scenario where you would write that, and I'm saying you should write it like this. Okay. For engineering purposes, I think it's just more natural and ultimately less bulky. And so, now again, there are great reasons to do it like this. It's beyond this course. And so, I don't want to go down that road. Is that satisfying?
Yeah, and just to confirm, we use that when we're looking at some form of a plane versus...
So no, don't think of it in terms of when should you use what, right? Write down true stuff, and then what you should use will naturally be a consequence of that, right? So the reason that we write down this is because we have if you're computing, let's say, flux of some fluid, it's because if you just forget about, don't think of it as a choice. Think of it as, look, we computed how to do flux on little flat pieces, and we add them up, and this is what you get.
Okay.
It's not a choice. It is imposed upon you by reality.
Okay.
Does that make sense?
Yeah.
So don't think of it as a choice. Think of it as, I got to write down true stuff, and the true stuff leads you to this. Yeah. It's a great question. Okay. All right, moving along. Let's be quick about this one. You could probably guess every word I'm about to say. Symmetry theorem, right? Odd integrand symmetric domain, integral is 0. Same warnings, right? They both have to apply. You got to use the same plane for each. It's exactly what you think. And I encourage it. I think symmetry theorems are awesome. And we now have a symmetry theorem for surface integrals. Just like what we had for line integrals, just like what we had for double integrals and triple integrals and single variable integrals, it's all the same. Okay, and same asterisk. This only works for scalar surface integrals. If you try to make this idea work for vector surface integrals, it crashes and burns badly. There is no odd symmetry theorem for vector surface integrals. And the reason why, you can look at your DS. You can see, you can see that orientation unit normal. You remember the whole point to a symmetry argument is that corresponding pieces on opposite sides cancel. And so everything in the expression needs to be either exactly the same or exactly the negative if you're going to have the cancellation happen. And it just doesn't happen here. These unit normal vectors are not the same. They are not negative.
they're just different, we lose. Right? So the reason this is a danger, of course, is that it's tempting to just go around citing symmetry theorems willy-nilly because they work so powerfully and we're so tempted to want to save ourselves trouble, etc. You just got to remember, for vector surface integrals, there is no odd symmetry argument. Side note, if you're wondering, you look at these two normal vectors, they're not the same, they're not negatives, but you know what? They are kind of, there's a relationship there. That is not random, right? You can go down that road and find a different kind of a symmetry theorem. And I don't want to talk about exactly what the correct, what symmetry theorem can you make there, because I've done it before and it's just more trouble than it's worth. Right? You can get yourself into more trouble than you can get yourself out of. Right? So I think it's a bad road to go down. But FYI, yes, there is a theorem down that road. Let's not mess with it. Okay. This is a neat little page here. You probably noticed already when we were talking about vector line integrals and when we were talking about vector surface integrals, in both of those conversations, we talked about how, it's basically differential forms. And that, in the context of describing coordinate line and surface integrals, they're basically differential forms. Integrals of differential forms. Well, okay, so that means they're two special cases of the same thing. Even though they come from totally different physics problems, right? Line integrals, we motivated by work. How do you compute work? Surface integrals, we motivated by flux. Right? One scenario has forces. The other scenario has a flowing fluid. They're totally different physical scenarios. Very surprising that the expressions we get are both special cases of the exact same construction. So anyway, here's the thing. When you're talking about basically the same thing, hopefully no surprise that they actually kind of line up pretty well. And so I think it's a fun exercise to kind of talk through some of that. So I only have so much width on my page, and so I had to kind of squeeze by having these arrows go somewhat down. Sorry about that. That's just layout. Right? I didn't want my writing to be too small. So anyway, in both cases, we parameterize. In both cases, we take the derivative of that parameterization of some sort. We look at the velocity there. We look at, the partial derivatives and then cross them that involve derivatives there. And if you look at how the velocity vector shows up and how the normal capital N vector shows up in the resulting equations, and by the way, the equations I have down there, it's all old news. Every single bit of what's written down on that page we've written down previously. It's all established. And notice, weirdly, the derivative of the parameterization, whichever one you're talking about, they show up in totally analogous places. And this analogy just keeps on going. So the unit tangent vector, the unit normal vector show up analogously. The vector differential, the dr vector in that case, the ds vector in that case, show up analogously. The magnitude of said vectors, namely the size. Oh, let's see, what color can I use? Oh gosh. I'll use light blue. How about that? The length of the dr vector, the length of that little piece of curve, the area of that little piece of surface show up analogously. Everybody see what I'm talking about? I mean, that's weird. Right? So if you came at this from the point of view of, well, look, we're looking at physics problems and we're going to write down, mathematical tools for computing work and flux, and you're just interested in the physics, and you write down a bunch of equations, well, that's, it's fine and everything, but you would never notice, you would never expect this level of analogy to show up, right? So to me, this is a jaw-dropping surprise. Huge, huge surprise. And so there's two upshots. One, it's a cultural point, right? This is one of the cool things about, if you come and take a class at Duke, you're going to get little tidbits that you wouldn't get, in a lot of multivariable calculus classes. And the fact that these analogies are this strong, and ultimately the big picture of why these analogies are this strong. They're this strong because we're talking about differential forms. It's all the same stuff. It's a neat thing to know, right? The second reason I like to point this out is that knowing there's such a strong analogy can help you actually in two ways. One, it can help you organize the ideas in your mind. Right? In some sense, you don't need to know two different stories. You just need to know one pattern, arguably. There's a point of view there, right? And secondly, aside from mental bookkeeping, you can use the analogy to help you understand things that maybe you are having a little trouble with. So just a thought for your consideration. But maybe if you're a little uncomfortable with the idea of what is the role that capital N plays and how should I think about capital N, well, it plays a role, apparently totally analogous to the role that the velocity vector plays. It's computed from the parameterization. It points in the direction of the orientation, plus or minus, depending on whether you did it upside down or backwards or forwards. And it's the thing whose magnitude is your stretching factor. They play exactly the same roles, right? So what you understand about the role that velocity plays in line integral calculations is a kind of a tip of how you should think about the role that capital N plays in flux integral calculations. So again, it's kind of a learning tool in that sense.
Okay. By the way, the pattern continues. All this stuff, I don't have time to. It'd be fun to play with the colors and do it all. The color pattern again continues perfectly. Be a fun exercise if you're so inclined. Okay. So moving along into 7.3. This is another monster section. It's going to take the rest of today and all of tomorrow. And I hope we can get it all done in those 2 days. I'm hoping we can leave Friday. We're off on Thursday, of course. But hoping we can leave Friday for the Chapter 4 stuff. But we'll see how time goes. There's a lot to say in this section. There are two big theorems to be discussed. Gauss's theorem is a huge one. Stokes' theorem is a huge one. And here's the good news. We are so set up. We've got everything lined up really, really nicely to talk about these theorems. We've already established the meaning of almost all of the players. We know what flux is, right, for example. And we know about the patterns, right? So a couple of patterns I'll remind you of, going back to the diagram. Right, we talked about, for example, with the fundamental theorem, how there's this sort of a pattern way to think about the fundamental theorem. You can suspect heavily that Gauss's divergence theorem should probably do something like that and should therefore probably, I would expect, look something like this, right? Purely based on the pattern, not even knowing if the theorem is true or not. You would be reasonable to guess that this is true. So again, let the diagram be your guide in a lot of ways. By the way, analogously here, different ways, but let's see here, back to here. And we already have this pattern set up about accumulating quantities. And again, this such an important idea. I think it's fair to say that if I could control what you remember from this class 20 years from now, if I could only have 3 things that I could guarantee you would remember, right? One of those 3 things would have to be this idea that when you have an accumulating quantity, you can think of it as a stuff, that it has a corresponding density, and you can write down a corresponding integral theorem. It's so huge. All of these theorems we're talking about fit that mold, right? So we're just going to go down that road 2 more times. So here we go. As you can probably guess, if we're going to talk about boundaries are oriented, and we have to establish what the rules are, right? So standard convention, it's arbitrary but standard. Here's the convention. The orientation is away from the solid, right? If you have some region R, and if you want to talk about the boundary, and that boundary needs to be oriented, the rule is, whatever you're taking the boundary up, orient on the surface in whichever direction points away from the solid, the meat of the solid. Common misunderstanding. A lot of people say always outward. Not true. Oversimplifying. Case in point right here. Right? That's not outward. That's inward, if anything. Right? So, okay, watch out for air bubbles on the inside. No air bubbles. Right? You're talking about the outside part of the boundary, outward. But don't forget the problem. Okay, and so now we're ready to run. And we have a new accumulating quantity, and it is boundary flux. Boundary flux is an accumulating quantity. It accumulates over volumes. If you take a volume such as this volume here, right, and if you split it up into chunks, like I have in I got the light gray on the left, I've got the dark gray on the right. Does the boundary flux accumulate? Is the whole the sum of the parts? Well, the big question, as before, is going to be this cut face, where it shows up twice, and as part of the boundary of R1, it's oriented that way. And as part of the boundary of R2, it's oriented that way. And we have the same integral twice with opposite orientations, and they cancel. And we've seen that several times previously. Everybody good? Saw this with Green's theorem. Kind of saw it with the fundamental level line integrals. By the way, we saw it previously also with 2-dimensional boundary flux, right? You remember we had this, where's my, there we go. 2-dimensional divergence theorem that we talked about as kind of a special case of Green's theorem, until I made this observation that, hey, boundary flux is an accumulating quantity. Notice it's morally the same picture. It's a 2-dimensional version of kind of exactly the same picture. And so the whole is the sum of the parts on any individual piece. Stuff is stuff per unit size times size, aka density times size. Okay. So we're going to be doing basically the same thing here now, 3 dimensions, but we are going to talk about how it's an accumulating quantity. And let me run through real quick to hit the highlights so you see the pattern. It behaves like stuff. It has an associated notion of density, for which we're going to have formulas, blah, 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 some interpretations, and then we can put it together to form a theorem. It's the exact same pattern. Okay. Now, I do want to go back here real quick and talk about a couple of details. I want to recognize that this is a big ask, right? And I've appreciated in the past that yeah, that's a lot to ask because flux is computed on the boundary, right? If you look for the formula, how do you write down flux? You compute flux by looking at a boundary. You're just entirely on the boundary. And I'm saying that even though it's computed on the boundary, yeah, but you want to think of it as being a stuff that's actually distributed throughout the interior. And, you know, that deserves an askance look. Because it doesn't seem like it ought to be, right? But big ask though that is, this thing called flux, it is an accumulating quantity. And even if it doesn't present as stuff, it behaves like stuff. So you can choose, counterintuitive though it may be, you can choose to pretend, to believe, right, that it is a kind of a stuff. And everything works out great. So, okay, all right. And then, of course, another reminder, with the fundamental theorem of calculus, again, same deal, right? So change is an accumulating quantity. And with change, again, you compute it on the boundary, but it not only can you think of it as happening in the interior, it obviously happens in the interior. So, hopefully that helps a little bit. By the way, I have another make it go down easier point that I'm going to be making in a few minutes. So we will get satisfaction on that. Okay. All right. The density, and again, I don't want to get into the weeds on exactly where it comes from, but first of all, when we say flux density, what we're talking about is stuff per unit size, just like when you're talking about mass density. Mass density is stuff per unit size. Same idea. Different quantity. Different kind of a stuff. Same basic idea of a density. And this flux density can be computed. And again, there's a bunch of details there, and I don't want us to get lost in the details. So I'm just going to say, look, here's your formula for flux density, as it turns out. And y'all can totally do those details. It's in the book. Just take a glance. It's just a little calculation. It's literally a computation on a little piece of volume of how much flux there is through the boundary of that little piece of volume, and then divide it by the volume. It's a straight up direct calculation, and this is what the answer ends up being. So suit yourself if you'd like. And then we have various terminologies and notations. So divergence is a common term. Flashback to chapter 3, an obvious sort of abbreviation of that term. And again, back in chapter 3, we talked about this del dot notation, which is extremely common and very convenient in several ways, and strongly encouraged. I like that a lot. Cool. Real quick, before we put it all together, let me remind you, because it is a density, right? Flux density is a density. It tells you where and how much stuff is happening wherever you might happen to be in the interior. So here's sort of the easy example. And you remember we did a sort of a dumb example analogous to this back in chapter 6. Silly example where we had a function that was changing. And we asked, which point in the interior is that change happening more? And we had the audacity to suggest that this accumulating quantity and its associated density, that would tell us where the function's changing. And then you look at the graph and you're like, yeah, it's perfectly obvious. It literally, the density, aka derivative, tells you where the function's changing and how much. And so, same thing here, weirder, but just as valid. If you want to know between these 2 points, where is more of the flux happening? Is there more flux happening at A, or is there more flux happening at B? Counterintuitive, because again, flux happens on the boundary. Flux is computed on the boundary, feels like it ought to be thought of on the boundary. I'm claiming it happens in the interior. And I want to know where more of it is between these 2 points. And well, if you want to know where something is, you look at the density. Divergence is flux density. That tells you where the stuff is. There's your formula for divergence. You plug in the 2 points, Right? And you get these two values, and if you want to know where is more happening, well, more is happening where the density is bigger. Right? It's totally like this example that we did back in chapter 6, this example right here.
And the function is changing. There's a total change between the starting point and the ending point. And the density algebraically tells us where there's more of that stuff happening, in this case change. And again, you can see it right there in the picture. So it's an object computed on the boundary, but we are realizing it as something accumulating over the interior, and the density tells us literally where and how much.
Okay. All right. Okay, so all of that said, put it all together. Here's our theorem. We have this quantity called boundary flux. It's an accumulating quantity. The whole is the sum of the parts, as we established. And on any individual piece, any little piece of flux in the interior is density times size. Stuff per unit size times size. Okay. All right. The disclaimers and worries, we'd have regularity issues, and you got to make sure there's no singularities. In a couple minutes, we'll talk about what happens if there's a singularity. Okay. Okay, first, let's get a computation under our belt. Let's do one. As a computational tool. Here we go. Let's compute this flux. We have a vector field given. We have a surface given, and we want to compute the flux. Now, for the record, we do have plug and chug tools for computing flux. Parameterize the surface, pull back, use the stretching factor, totally do that. I really, really don't want to. It'd be a nightmare. Let's just take a moment to recognize what a nightmare that would be, right? Think about it. When you parameterize the sphere, how do we parameterize the sphere? Well, with spherical coordinates, and that means trig is coming up all over the place. X, Y, and Z are chock full of trig. And now let's imagine how much ugly gets created when every single X, Y, or Z in this vector field is going to be just explosion of trig. Right? It'd be a nightmare. Okay. All right. Okay, well, so let's see here. Our surface, S, is the inward-oriented unit sphere. So here's our surface. Is that a boundary? No. Tragically, not a boundary. Boundary is a delicate and finicky word. Boundary means oriented according to the convention. This is not. That is not a boundary. The orientation's wrong. But we're going to use the same little trick we pulled previously, which is that it sure does look an awful lot like this other surface oriented outward, which is a boundary. And the only difference is the orientation is different. Right, so we used a morally equivalent trick back when we were doing Green's theorem. Right? So, yeah. So our surface is just the opposite of what you get when you orient it the opposite way. So don't forget that minus sign. And now it's all over. Here we have an integral over literally a boundary. Here, let me do it like this. This is literally a boundary, and because it's a boundary, I can compute that integral with Gauss's divergence theorem. Everybody cool? And it's all over for the shadow. So much better than trying to do this with a pullback through a parameterization. I'm probably intractable. I don't even want to, it's too scary to even contemplate. Okay, so really cool tool. But I do want to point out, this is another little sort of computational sort of, cool trickery. But this right here, that integral, oh gosh, the integrand's not constant, so I can't make a geometry argument. It's not symmetric, so I can't make an oddness argument. That integral, as written, no cool tools apply. But there is this cool thing that happens that, if you just take these two integrals, if you or take this one integral and break it up into two separate integrals, the one on the left is easy geometry. The one on the right, zero by symmetry. So heads up for that. This is another big trick that I used a lot when I was in y'all's, stage, and I imagine this will work for y'all as well. So just, again, I'm not saying it always works, but I am saying it's very useful surprisingly often. So you want to be on the lookout for fortunate details. By the way, also, make sure you flesh out this argument. Think it through. Remember, symmetry arguments are delicate, therefore dangerous. So make sure you can flesh that out. Talk to me in office hours, of course, if you have any questions. Everybody happy? Okay. Now, let's talk about physical examples. And there's so many cool ideas in here, and I'm not going to have time to tell you everything, but I'm going to tell you what I think are the biggest, coolest ideas. So this is my favorite first example. It's not the one that you're going to use the most, but it is a fabulous for what I feel like are pedagogical reasons. There's some really neat ideas that you can deal with this example. So we're going to imagine a light bulb. Yeah. Okay. Well, what do light bulbs do? Well, they generate photons that then flow outward, and it's a kind of a fluid of sorts. Now, it's not a liquid, but it is a kind of a fluid in the usual sense, right? And if you think even liquids are just sort of collections of particles that are all kind of moving somewhat together. Well, that's what this is. Okay. All right. All right. Well, let's. How would we describe this? We've actually talked previously about the inverse square radial vector field. Now, this applies away from the LED. So where that little LED is at the center, this formula doesn't apply there. But away from where the LED is, this inverse square radial is valid for basically everywhere except, there's so much to fill in. Everywhere except for where the LED is. Okay. Let's think about what the divergence is. And what should the divergence be? What would kind of make sense? Well, you can take this formula and you can straight up compute the divergence, and what you're going to find is that the divergence is 0. Now that's everywhere else, so not the origin, right? But everywhere else, divergence is 0. Y'all may have already done that calculation back in chapter 3, I think. I can't remember. But anyway, if you haven't done that calculation yet, it's a good sort of, training exercise, right? If you have, then no need to do it again. Okay. Now here's what I think is a really cool argument. It's one thing to compute and get 0. Let me now show you why you should expect to get 0. I claim that this is a satisfying answer as follows. Keep in mind what divergence is. Divergence tells you flux per unit volume. And now that we know that, I can say, all right, well, let's look at some region. Let's say right there, some little three-dimensional ball with a boundary sphere. And let's talk about the flux. We've got a light bulb there. The light bulb is shooting out photons. Some of those light bulbs will create some flux on parts of this boundary surface, but here's the thing. Every photon that goes in also goes out. It's a very simple observation. Every photon that goes in goes out. Every photon that goes out must have previously gone in. So therefore the outward flux on the sort of the outside and the inward flux sort of on the inside, they have to cancel perfectly. The flux has to be zero. Everybody good with that? Well, there's no flux and there's no flux density. So not only is the divergence zero, it should be zero. It's once you digest this point, once you get really comfortable with this idea that, look, everything that goes in goes out, as simple as that, I want to say it's obviously zero. Once you digest this point, once you fully get that point, yeah.
So, I mean, light gets less intense as you go further.
Yeah.
And so, wouldn't it be that what's going outside has a lesser magnitude than what's coming in?
Yeah, but there's slightly more area. Yeah, right? Because the rays coming out are not parallel.
Mm-hmm.
Yeah. No, that's exactly right.
Yeah.
And exactly balanced by the counterpoint. And now again, that's it's always good to think of things from as many different points of view as possible. On the other hand, it is also always good to, when you find that one point of view that makes the whole problem just disappear, go with that one, right? And I think what I'm presenting in terms of everything that goes in goes out. I mean, it's hard to argue with that, So yeah.
So since there's no flux,
Yeah.
so then is much of it just accumulated?
Do what now?
Is the much of the photon density accumulated at the center?
Well, now the photon density is a different thing, right? And I hear what you're saying, right? That you would think that flux would be, if you got stuff and there's flowing outward, or if it's flowing inward, or that somehow the flux would affect the density. But importantly, that's just not what happens, right? And now I appeal to your intuition about, look, we're surrounded by light bulbs here. And there's no photons collecting anywhere, right? So we're going to make a different interpretation of divergence. In particular, if you look at this region here, however many photons there are in there, how many photons there are in between, let me get where a light bulb can see me, right? The number of photons that are in between my hands, it's not changing. It's pretty much fixed. And now there are different photons now as opposed to now, right? The original photons are long gone, and it's a different collection of photons, but it's the same number pretty much. So yeah, does that make sense? Okay, big idea. Now let's apply that idea at the center. Let's see here. Keeping in mind the center is a light bulb. And now, instead of considering a region like that, let's consider a region like this. Right? And again, this is a solid region with a boundary sphere. What's going to be the flux through that sphere? Rhetorical question. Can I say that everything that flows out must have flowed in? Actually, in fact, no. There is a photon generator inside of that region. The photons that are flowing out did not flow in. They were created in there. Right? So, okay. Short answer then, a pithy rephrase. If I want to know how many photons are flowing through that boundary surface, the crisp answer is all of them. Every photon that gets created becomes flux. Doesn't even matter how big that sphere is. Right? It's just, whatever the wattage of the bulb is, or I guess the lumens is maybe the more relevant. Right? However many lumens you've got, that's going to tell you exactly what your flux is.
How many photons flow through the surface? All of them. It's that simple. So now let's talk about divergence. Okay, well, this sphere can be whatever size. I mean, big sphere, small sphere, still all of them flow through that boundary. If I want to know flux per unit volume of where the LED is, that sphere is going to have to get really small. It's going to have to be as small as the LED. And they're itty bitty little things. They're, a couple of millimeters? Teeny tiny. So, at where the LED is, we have large flux per teeny tiny volume. And so we have a huge flux per unit volume and therefore a huge divergence.
Okay. All right. Now my last point on all of this is, as I claimed, this is a wonderful metaphor for understanding this, for digesting this idea that divergence actually happens in the interior. That flux happens in the interior. We have, let's see here, okay, I'll use... Okay, so if I were to look at some sphere like this and ask what the flux is, and we do a computation that happens on the sphere, and I get a certain amount of flux. Okay, where did that flux come from? Well, where that flux came from didn't come from any of these points. Flux density, divergence, is telling us that there's zero flux density there, so that's not where the flux came from. This, where the divergence is pointing to where the flux comes from. And it not only does it give us an answer, it gives us the obviously correct answer. It's telling us literally where the flux on this green sphere is coming. That flux didn't come from the sphere. Right? Where did the flux come from? The flux came from the ball. It came from where the photons are shooting out of. That's where the flux was made. We just didn't notice it until it got here. Is that satisfying? Everybody on board? Right? So in the same way, I think anyway, in the same way that, that's not the picture I wanted. Oh gosh, hang on. That the derivative is telling us where in the interior the change is coming from that we detect on the boundary. And when we detect change on the boundary, yeah, sure, that's how you compute change. You value here minus value there, yeah, of course. But where did it actually happen? Well, change density literally tells us literally where it's happening in the interior. Is that cool, right? And this is just a different sort of metaphor that gives us what I'm going to call the same satisfaction. Right? Divergence is telling us that's where the flux is coming from, not there. There. I find that very satisfying. And again, it to me, the big ask. Right? Oh yeah, it happens on we measure it on the boundary, but I'm going to try to ask you to believe that it's actually coming from the interior. Yeah, it absolutely is in this example. Okay, good stuff. All right, now let's talk about singularities real quick. So this is basically, it's what I'm going to call a limiting case of the previous example. Imagine a light bulb where imagine how technology is going to develop over time, and LEDs are, small now, but they'll probably figure out some way to make them even smaller, and then even smaller, and then eventually they'll be, you can imagine this limiting scenario of what happens when the LEDs approach no volume. Smaller and smaller and smaller and smaller. Okay, well, then this formula applies everywhere. Pretty much, other than, obviously there's something bad happening at the origin, but everywhere else, right? This is what the vector field looks like, and again, y'all have already computed the divergence, and the divergence is 0. So the divergence is 0 pretty much everywhere, except for that one little point. Yeah. Well, we also know that if we're interested in the flux through some surface, and let's look at this surface here first. On that how much flux is there through that surface? How many of the photons created by the light bulb at the origin, like the little point light source at the origin? How many of those photons pass through this surface? All of them. Exactly all of them. And by the way, you don't even have to worry about the lumps, right? So it's a simple story for a photon that flies out like that because it passes through the surface exactly once. But you might be worried about what about a photon like that, because it passes through 3 times. Isn't that going to mess up the calculation? But it doesn't, because as flux, that one's outward and therefore positive. This one is inward and therefore negative, and this one is outward again and therefore positive again. So again, it in the net passes through once. So the flux is entirely determined by the lumens of the light bulb, so on that green surface, flux is, right, it just depends on K. K basically is telling you how bright your light bulb is. A couple of details you got to work out, and it ends up being 4 pi K. Okay. On the other hand, if you're looking at a surface that doesn't contain the light bulb, keeping in mind the light bulb is right there, and if we look at, let's say, this surface, what's the flux through that surface? And I claim 0. Because, well, every photon that flows in also flows out. Again. So 0. Everybody happy with that? Okay. So with this in mind, now I claim we're prepared to kind of at least address this idea of what's the problem with a singularity. And the problem is, hey, wait a minute, I thought Gauss's divergence theorem told me these things are supposed to be equal. And wait a minute, didn't we just compute that the divergence is 0 everywhere except for that one teeny tiny little, come on, just 1 point. It's just the 1 point where the singularity is. I mean, surely, does this one single point mess things up? Why, yes, it does. Because sometimes these are really different, right? I mean, the triple integral would appear to be 0, but the flux is actually very much not 0 sometimes. Right? So this is what a singularity can do. Singularities can mess things up. Now, in this case, there is a take. There's a kind of a takeaway. I've been pushing this idea that flux is distributed over volume, as if it's distributed in a sort of a uniform, sort of per unit volume kind of way. But what we have here, everything is behaving as if there is a discrete lump of flux, like at the origin, exactly where the point light source is. It's like instead of having a distribution of flux over the interior, the stuff of the flux, instead there's just a single point of flux. And so if you take that point of view, then how much flux is there in the green region? Well, there's some definite flux there, and it's adding up. It's coming from the origin. And then what about in this blue region? None. Doesn't contain where that lump of flux is. Right? So anyway, that's sort of a takeaway. This interpretation doesn't always work. I'm not saying that every singularity can be thought of as a lump of flux, but in this case, it kind of can. So anyway, all right. Okay, flowing of a gas. Now this one's arguably easier kind of fluid to think about, but I want to make the observation that this is a qualitatively different fluid. It's a very, very different kind of fluid. We're imagining that there's a certain amount of gas. Maybe this is a nebula out in space or something, right? And we've got a certain amount of gas, and for whatever reason, the gas is expanding. Let's just imagine there's a finite amount of gas, and the cloud is getting bigger and bigger. Okay, well, if you got a finite amount of gas, then it is not being created or destroyed. That's very different from our previous example here. Light does not work that way, right? Light is literally being created. Right, so that fluid gets generated. This fluid does not. And there's another big difference, which we also talked about. In this case, obviously, as the gas is spreading out over more and more volume, the density is going to be decreasing, but not with photons. With photons, the density is what it is. It's time independent. However many photons per unit volume there are between my hands, that value is not changing. Does that make sense? So very different kind of fluid. All of our interpretations we have to kind of redo because it's just it's a different deal, right? And here's the way I like to think about it. We know, and if I were to ask, let's imagine some whoops. Where's my? Oh, and my pen died. Okay, as it likes to do. If I were to imagine some sphere like that, right? And if I were to ask what is the flux through that sphere, well, divergence theorem, compute the divergence, boom, there's what your flux is through that sphere. And now I'm going to make another sort of qualitative argument, which is that the flux is telling us how fast fluid is leaving the ball. I argue that that's what the flux is. The flux is literally just telling you how fast is mass leaving the ball. And so the more flux there is, the more negative the rate of change of mass is. Does everybody buy it? Yeah. Mm-hmm.
What do you mean by the K on?
Oh, this was just this is just a formula for this vector field. That's the vector field of the fluid that we're actually the flow of the gas, and it's just that's modeling this idea of the gas kind of expanding outward. Yeah. Right. Okay, so this is an important interpretation of flux, and we talked about this in the context of like herds of zebras or something long ago. That flux is the act of stuff leaving from one side of the border to the other side of the border, and so flux really is telling you how much you're losing your stuff, right? Whatever the stuff of the fluid is. All right. Well, with that, take, and then don't forget that mass is a integral of density, and then of course you can take this derivative and kind of pop it in there like so, and check it out now. We have an integral here that is equal to another integral over the same domain. And that this works everywhere. It works for every domain. And how could that possibly be? We have two different integrals that always give the exact same value? Come on. There's only one way that's possible, and that is that the integrands must be the same, and so that means that we have an interpretation of divergence in this context.
different kind of fluid. In this context, divergence, whatever that ends up being, is telling you the negative of the rate of change of the density of the fluid. For this kind of fluid. Different interpretation. It's not at all the interpretation we had for the sort of the generating, the photon flow, light bulb type fluid. Totally different interpretation because, again, it's totally different stuff. All right. Okay. Now here's where things get weirder. Sometimes you have both in play. There are some fluids where the fluid is being generated and simultaneously the density is changing. In other words, it's sort of a combination of both the sort of the unique features of the photon, sort of light flow, light bulbs type fluid, and the expanding gas fluid. So it just has an easy example. I mean, by the way, my picture is weird here. This is I can't help it, right? But I've drawn a two-dimensional region here, but you have to kind of use your imagination. This is supposed to be Rn. I have to draw Rn as two-dimensional because I need to talk about stuff coming into it from the outside, and I can't draw the outside of three-dimensional space. We can't understand that way. That's not something we're cut out for. So just imagine what I've drawn as a plane here is actually in dimensional space appropriate to whatever you're considering. And sometimes fluid is entering from the outside, being generated, in other words, and sometimes fluid is going outward like that. Now, where's the scenario where this happens? And an easy example is just pretend that the plane here is actually a plane. I like to think of it as being like a slab of concrete. Imagine that it's raining. Right? So if our fluid is the water on the slab, raining is effectively creating new water to flow around on the slab. And as it rains and as the water flows around, the amount of water per unit area on the slab might very well be changing. Okay? Here's another easy example. Let's think about some species of animal, squirrels. There's a bunch of squirrels in my yard. Right? A bunch of squirrels around campus. And you can talk about how many squirrels per unit area there are. Right? Well, over time, not over hours, right, but over years, two things happen. The squirrels might move around. The squirrels might, they used to live here, but now they live over here. They moved to more trash cans, more free food or whatever in some area. And so they might move, and squirrel density might change. And over years, there is a generation of squirrels. They have baby squirrels. Right? So we're literally generating the fluid called squirrels. Right? When they die sometimes too, right? It's very sad, but that's a negative of generation. So this is very practical, very natural, comes up all the time. And anyway, I make the modest observation here that however much fluid is being generated, however much fluid is coming in from the outside, that is a positive contributor to the amount of stuff in your region, right? And to whatever extent the fluid is leaving, to whatever extent you have flux, that is a negative contributor to how much stuff you have. How many squirrels are in your region there? Well, flux means you're losing squirrels, and G means they're having lots of babies. Is that cool? Yes.
So your dm by dt is always going to be in Rn minus 1. Or is
No,
it?
it's in RN. Yeah.
So this M here is a reference to how much of whatever the fluid is in our region at any given point in time. The flux will be an integral over the boundary, which is n minus 1 dimensional, but the M is the amount of fluid actually in the region. Yeah.
So
Okay,
M is
yeah.
like a quantity.
Yep. M is that's right. M is how much of the actual stuff. How many squirrels?
M has to accumulate, yes?
Oh yeah, absolutely. All of this is only for yes, absolutely. Yeah. So non-accumulating quantity. We got nothing. Can't deal with that. Right. Absolutely. Okay. So now I will point out that while we can talk about the grand total amount. Altogether, the grand total amount that fluid is being introduced. We can also talk about where it's being introduced. And so, for example, sometimes it's raining over here, but it's not raining over there. Right? And altogether, this this G, the grand total amount of fluid, is an integral of a density. As it's a little bit weird to talk about, but this is an integral of generation per unit volume, which I'm going to call generation rate density. And of course, we also know that flux is a triple integral of divergence, and we know that mass is a triple integral of volume. So this equation that we have here, this equation here, which I rewrite like so, I can further rewrite like so, and now again, look at this, these integrals, they're all over the same domain. So the relationship between these integrals is also a relationship between the integrands, and we get what's called the continuity equation. So this is an equation that basically this is what tells you how to make sense out of divergence depending on what the nature of your fluid is. And some easy special cases. We've already talked about two of these special cases. If there's no fluid being generated, that's our expanding gas example. If there's no fluid being generated, okay, well then the continuity equation tells you what we already knew, that divergence is the negative rate of change in density. Yes?
So, like, back when we were studying the vector fields, when we were learning about divergence, you said, like, the same concept about stuff being created versus, like, density being decreased. So, does this tell you, like, exactly whether, like, how much is actually happening?
I'm sorry, I didn't follow your question.
Does this tell you, like, whether, like, how much is created and how much is, like, decreased at the same time?
Yeah, well, it's not telling you either. It's telling you the combination.
Right? So divergence, divergence is telling you kind of, if you will, G minus the rate of change of density, right? If you solve for divergence. So you're going to have to know more information. Like I have to have some understanding of what G is to conclude the relationship between divergence and density. And I would have to have some understanding of the rate of change of density to understand the relationship between divergence and G. Right? So I mean, it's not a single thing, but this is the relationship between the objects involved. And so when you have specific information, such as if G, I wanted red here. If G is 0, if you have that extra knowledge, then you can draw a conclusion like we do here. And then, by the way, on the flip side, if I were to know that density is constant, and this is the light bulb example, in the light bulb example, there is no changing of photon density, and then I get a relationship between divergence and G. All right, so you got to know one to be able to conclude the other. But
what's always the case is that these three things relate by that equation. Does that make sense? Yeah.
Okay. All right. So really neat stuff. Oh gosh, and let's see. I appear to be out of time. Okay, I am out of time, so we will draw the line right here, and we will figure something out about how to finish all this material. See y'all on tomorrow. Yeah, see you tomorrow. Have a good one. Okay, bye.